All right, in Calc 1, if you want to find the area under a curve, you use integration. So for instance, you have the function y equals f of x, and then you want to find the area from x equals a to x equals b, and this is x. So you'd like to find this area here. So it's quite clear that the integral is the integral from a to b of f of x dx. You know what? I would like to use a different variable. I'm going to use the variable t for some reason because we're dealing with parameters now. But think of t as your x. So let's call this axis t axis, and let's call this y axis. Doesn't matter. It's the same thing. So another way to write this integral is that a is the integral a to b right here. So this is just a different notation. I'm sure you've seen it, or maybe you haven't. It's not popular. Okay, but the whole thing, the setup here is that we're integrating along the horizontal axis, along the x-axis, which in this case we're calling t. Just a different name. All right, now, this is in R2, what we know about in R2. Now in R3, think about a random line in R3. So that z-axis, x-axis, and y-axis. All right. Now, assuming you have a line or a curve, think of this curve. It's a curve in space, a curve in the XYZ space. And this curve goes from the point where t is equal to a to maybe t equals b. So this is a parametric curve that can be parameterized. Now, think about having a function above this curve. So we have a function. I'm going to make the function light blue. So we have this function above the curve. Okay. And this function right here is a function, so maybe it's a function of three variables. Think about it as a function of x, y, and z. Remember, since t is our parameter, x is a function of t, y is a function of t, and z is a function of t. That way. All right? Now, what we want to do is we would like to find the area on top of this little black curve. Let's call it C. But under the blue curve. So think of the blue curve as the same thing as the curve here. I'm going to make it blue, right? In R2. So we have the function in R2, but now we have it in R3. And instead of our vertical or our horizontal axis here, which I'm going to paint black, instead of our horizontal axis here, going from A to B, we have a curve that is no longer horizontal, it's just an arbitrary curve. And the whole point is to find the area under the blue curve but on top of the black curve from A to B. So we're looking for this area now. So T goes from A to B. So if you think of the t-axis, we can think of the t-axis as this. T equals A to T equals B, right? But now, instead of looking at the axis, the curve, as being proportioned in terms of t, we can think of it as being proportioned in terms of the length of the arc. What do I mean? If the length of the arc is in terms of s, for instance, so this point here might be s, where s is equal to 0, okay? The units of the length of arc, s is equal to s1. So let's do this. Let's call this S0, let's call this S1, maybe S2, all the way until Sn, something like that. Okay, and we're still calling this curve C. Our goal is to find a way to calculate this area A, this new area A. Let's do some development. Let's try to look at the relationship between S and T first. What do we know? We know that from previous section, we know that S of T is equal to the integral from A to T of R prime of T d tau, or let's call it R prime of tau d tau. Okay, and I'm going to explain this in a moment. Okay. All right, so let's assume that C is a curve that is parameterized. C is this curve that is parameterized as R of T. Okay. The length of arc of C goes from T equals A to T equals B. But why am I doing from A to B to T from A or tau from A to tau to T? Because we want to be able to capture the length of arc from any point to any point on the curve C. So we want to be able to go from maybe S0 to S1, maybe where S is equal to A to S is equal to T, assuming this is equal to T or something like that. So that's what we're trying to do here. All right. And we're going to talk more in class about parameterizing a curve in terms of S, where S is a parameter that denotes the length of the curve, the position of objects along the curve. All right, so if this is the case, we know that this implies that ds dt is equal to r prime of t, right? Magnitude of r prime of t. This is the fundamental theorem of calculus, part 1. Whenever you have an integral expressed like this is an integral from a constant to t. If you take the derivative of the integral, it just means you're just left with whatever is inside the integral. So we have that. Another way of writing this is that ds is now equal to r prime of t dt. All right. This is what we want. Okay. Now, we can go ahead and try to compute our area A. So this A now is equal to the integral from A to B of f of x, x of t, y of t, z of t, all right, ds, all right, ds. But now, ds, we can rewrite it in terms of dt, which is r prime of t dt. Okay. So that's our area. In other words, let's use this notation right here, right? Or let's try to create an analogy for this notation, right? One way of looking at the area along the curve is to just write it this way. One notation is to say, oh, we're looking at the area along the curve C of our function f right here, f, then we call it ds. And s is the position along the curve, s0, s1, s2, up to sn, all right? But it turns out this is the integral from a to b, just like we have there, of f. We can write it as f of r of t, magnitude of r prime of t, dt. And what is r of t? R of t is the vector that has x of t, y of t, z of t. So that's r of t. All right, when we do an example, this will become clearer, okay? So, but we can formalize all we've done in one simple theorem, okay? So, all the explanation I just made is like my attempt to prove the following theorem, you know. It's a little bit not too clear because this is Calc 3 and we don't have enough time to like explain everything from scratch, you know, develop everything from scratch. But I hope the little explanation I gave to you is good enough to make you be able to use this theorem. This theorem is just like a summary of everything that I've been saying so far. So we have the theorem. The theorem says let f be continuous on a region containing a smooth curve. C, and C is parameterized as, has the parametric equation x of t, y of t, z of t. For t going from A to B. Then the integral, the line integral of f ds over c is equal to the integral from A to B of f of r of t times the magnitude of r prime of t dt. Another way to write it is that the integral f ds is equal to the integral from A to B f of x of t, y of t, z of t, x prime of t squared plus y prime of t squared plus z prime of t squared all enclosed in a square root dt. So these are the formulas we're going to be working with. These are the important formulas. All right. So in this section, we're concerned with how to compute a line integral. A line integral are just the integral over the curve C, the black curve which we looked at before. Black curve. Instead of integrating along a horizontal line, we're now integrating along a curve in R3. The integral over this curve of f, a function f, ds, where s is a way of noting the position along the curve, ds. So this is called a line integral. All right, there's another thing I want to point out. A smooth curve. What is smooth? Smooth in this case, smooth here means that there is no edge. It means C has no edge. The curve C has no edges. And it also means that R prime of t exists. And R prime of t is not equal to the zero vector. So that's what it means. Okay, so the takeaway is that we have a way to compute line integrals now. Let's look at some examples. Let's evaluate the line integral x of x sine z ds, where C is a circular helix given by r of t equals cosine t, sine t, and t goes between 0 and pi over 2. So what do we have here? What are we trying to do here? We have our circular helix. We have a helix that goes from here to there, right? And this helix is C. And we have a parametric equation for the helix. And we want to compute this integral right here, okay? So we're going to be using the formula f ds. Remember this, it's a to b, f of r of t times r prime of t dt, okay? So we have to find each of these things. What is our a? What is our b? Our a in this case is 0, 0. Our b is pi over 2. We need to find our f of r of t. We need to find r prime of t, and then we need to find the magnitude of r prime of t, and then we're good, okay? So let's go one by one. Let's find r prime of t. We have r of t. R prime of t is equal to negative sine t. That's the derivative of cosine t, and then cosine t, and then 1. And then we need to find the magnitude of r prime of t, which is the square root of negative sine t squared plus cosine t squared plus 1. Sine squared t plus cosine squared t is 1, so this is just going to give us square root of 2. Okay, so let's go back. We have almost all the things we need. We now have that the integral, the line integral of x sine z ds, okay? So our f, this is our f right here is now this. Okay. Now, we need to go from A to B. A is 0, B is pi over 2. F of r of t is to substitute r of t into x sine z. What is x? X is cosine t. And what is z? Z is t. So sine z is sine t, right? And now what is ds? Or what is ds actually? ds is the magnitude of r prime of t dt. So magnitude of r prime of t is square root of 2 and then dt. Okay. All right. So this integral is something you can easily handle. So I'm not going to waste time on it. Use u substitution, make u sine t, and then you're good to go. All right. The final answer that I got is square root of 2 over 2. Okay. All right. Let's try another example. Number 2, we would like to evaluate c, the line integral of 2 plus x squared y ds over c, where c is the upper half of the unit circle, upper half of the unit circle. Okay. So now we're in 2D. We're actually in 2D. We're in R2. So this is our C. All right. Our C is the unit circle, upper half of the unit circle. So if we parameterize our C, this is t equals 0, and this is t equals 1. Right? Or we can go from t equals 0, to t equals pi. That's better. And if we go counterclockwise, then our parameterization is going to be that x is equal to r cosine theta. R cosine theta, but r is 1 because the unit circle has radius 1, right? So it's just going to be 1 cosine theta, or cosine t in this case, and y is 1 sine t. All right, so we're almost good right from the get-go. Now we want f, remember f ds. This is your f in this case. This is your f right here. And your c is this curve. And the parameterization of your c is r prime of t such that such that x is cosine t and y is sine t. Okay. All right. So remember this, I'll keep writing this formula. Integral over c of f ds is the integral from a to b of f of r of t, magnitude of r prime of t ds. All right. I will let you calculate the magnitude of r prime of t. Okay. I'll let you calculate it, but the magnitude of r prime of t is actually 1, but I'll let you figure it out yourself. All right. So f of r of t is to just plug in cosine t for x and sine t for y in the function. So we actually want c 2 plus x squared y ds. This is what we want. So because this is now that is your f. All right. So to plug in r of t is to plug in cosine t for x and sine t for y. So we have 2 plus cosine squared t sine t. All right. Magnitude of r prime of t is 1. Right. Sorry, this is supposed to be dt. So we have 1 and then we have dt. Okay. I will let you calculate that, r prime of t. All right. This is an integral that goes from 0 to pi. Okay. And I will let you figure this out, but I got 2 pi plus 3 plus 2 halves plus 2/3. That's what I got. Okay. All right, you will notice that I did this problem assuming that we are in R2. Okay. If you want to do it in R3, just like we did the other one, then you can think about your C this way. Think about if you want to do it in R3, C will now be R of t such that it is cosine of t, sine of t, and 0. You put 0 there. So because you're just going to assume that you have your z-axis, x-axis, and y-axis, and then this is your upper half. It lives on the xy plane. So you can do that if you want. It's going to be like this. Okay. All right. Let's try another problem. Let's say okay. Number 3, 3a. Let's evaluate the integral of xy plus 2z ds. So that's the line integral, and it's on the line segment from that goes from P1, 0, 0 to Q 0, 1, 1. So first of all, what you want to do is you want to parameterize the line. So remember how to find the equation of a line segment in 3D. All right. So this line segment starts from the point 1, 0, 0. So maybe this point 1, 0, 0 to 0, 1, 1, 0, 1, 1, somewhere here. Okay. Okay. So this is where t has to be 0, and this is where t has to be 1. This is your P, and this is your Q. So what is your directional vector here? It's going to be V. You're going from P to Q. So 0 minus 1 is negative 1. 1 minus 0, 1, and 1. So that is your directional vector. So first of all, let's call this line segment R of t. So this line segment is our C. In this case, this is our C. Okay? So C is R of t, but R of t is the line segment that starts from P and ends at Q. Okay? So you go P 1, 0, 0 plus t times V. V is negative 1, 1, 1. And then T has to go from 0 to 1 because it's a line segment. Okay? So R of T, think of R of T as 1 minus T, negative T. Oh, no. 1 minus T, T, and then T. So that's R of T. Now let's go for R prime of T. So R prime of T is just going to be take the derivative. So you have negative 1, 1, 1. And then magnitude of R prime of T is the square root of negative 1 squared plus 1 squared plus 1 squared, which is square root of 3. Right? Now, what do we want in this world? For now, we want to be able to calculate this line integral. But we have all the ingredients now. We have that this line integral now, if you call this your f, if that's your f, then remember that this line integral is going to be the integral from a to b. Remember what's your a? Oh no. This is your a and this is your b. Right? It's the integral from a to b of f of R of T, magnitude of R prime of T dt. So how does that go? A to B, f of t is to plug in 1 minus t for x. So we have 1 minus t times y. Y is t times t plus 2t. That's what you get. Plus 2t. And then multiply it by square root of 3. And then dt. So this is going to give you, our a is 0, our b is 1. It's going to give you the integral, factor out the square root of 3 because it's a constant. And this is going to give you 3t minus t squared dt. This is a very easy integral that amounts to 7 square root of 3 over 6. I want you to try something, and you must try this. You must try this one if you're in the course. You definitely need to. Try. Actually, I'm going to make this a quiz. You want to try it, and I'm going to ask you questions on it. It's a quiz. All right. So, what is this quiz? Now, it's the same thing. Evaluate the integral from c xy plus 2z ds. And you want to go from q equals 0, 1, 1 to p equals 1, 0, 0. Okay. All right. I want you to try it, but I'm going to give you the answer. The answer, you should get the same answer that you got in A. So you're going to get the same result as A. So we have a line integral, so you're going along a path, so we're going along this path from P to Q. In A, we're going from P to Q. In B, we're going from Q to P. But the line integrals are the same thing. This line integral, so this line integral is C, and this, let's call this negative C. This is just a notation because we're going backwards. We're going to call it negative C. So this is a big result. Right? The line integral of fc ds is equal to the line integral of negative c f ds, right? Provided f is a scalar function. So scalar line integrals equal each other, as long as it doesn't matter the direction. If you're going from P to Q or going from Q to P, it's the same thing, right? And it doesn't just apply to straight lines. Assuming you have this line, as long as it's a smooth line, right? And this is C, this direction is C, right? And you have the same line, right? But you're now going this direction, negative C. It doesn't matter the path, you'll get the same thing. That's all I'm trying to say. But you still have to compute this. I will still want you to compute this integral to show yourself that you get the same result as in A. If you don't get the same result, something is wrong. Another thing I want you to try is this. Another problem. It's a word problem. You know what? This might be the quiz, but I'm not going to tell you. One of them is going to be a quiz in class. One of them. So I'm putting asterisks there. One of them will be a quiz. Try me, don't do it. And then you fail the quiz. All right. So this says the temperature of a circular plate R equals xy such that x squared plus y squared is less than or equal to 1 is given by t of xy equals 100 times x squared plus 2y squared. Now we want to find the average temperature along the edge of the plate. Average temperature along the edge of the plate. What do you want to do here? I'm going to give you a hint. This is your plate, right? That's the region of the plate. Okay? It's a unit circle. X squared plus y squared is less than or equal to 1. So it's a unit disk. So, but your plate now, the edge is now your curve C. So you're going from this point back to the point. So you want to parameterize it first. You want to parameterize your C. So what is C? C has to be R of T is equal to something. You probably know what it is by now. And where does T goes from? What's the range of T? T from 0 to 2 pi, all right? So what you have to compute now is the line integral. You're computing the line integral c, right, of f, but in this case is actually t ds, the temperature function. You know what? I'm going to call this something else. I'm going to call it something else. Oh, well, I'm not going to call it something else. We can confuse ourselves. T here is the temperature, but don't confuse it with T for tangent. We're going to be using T for tangent a whole lot. So you want to compute this line integral. How do you compute it? All right. Now, when you compute it, you want to divide it by the area of the disk. Of the disk. The plate. It's called plate in the... All right. So that's what you want to do. I want you to try it. Okay. Now, so we've been looking at the line integral over curves, but the line integrals we'll be looking at has been the line integrals of scalar functions. Now, how about the line integral of a vector field? Okay. So line integral of a vector field. All right. So we've been looking at integral, so scalar field is the integral f ds. But now we want to switch to vector fields. Will be the integral, line integral, c f dot t ds. That's what we want to compute. So you have the vector field. You're now finding its dot product with the tangent vector. All right? With a tangent vector to the vector field. Okay? How do you compute this? You want to go from A to B of F. Remember how to compute the tangent vector. Remember how to compute it. All right? We're going to think of T as the unit tangent vector. So this is going to be R prime of T divided by the magnitude of R prime of T. That's how we compute the unit tangent vector. And remember that ds, we obtained that ds is equal to R prime of T dt. Okay? So when you cross things out happily, this and this will cancel out, you end up that this is the integral from A to B of f dot R prime of T dt. All right? Okay. So we can summarize this in maybe a theorem. Let's call it a theorem. Or more explanation. Call it explanation or fact or summary. All right. If we let f be a continuous, a continuous vector field. Okay, it has to be continuous and it has to be defined on a smooth curve, on a smooth curve C, given by the vector function r of t, and r of t goes from t from A to B. Then the line integral of f along C. Okay? We want to compute the line integral of f along C. All right, so far what do we have? We have C. This is C, a smooth curve, and C has its orientation like this, and C, this is where t is equal to A, and this is where t is equal to B, right? And we want to compute the line integral of this vector field along C. Okay. But it turns out that this line integral actually means something. First of all, its notation is the integral f dot t ds. This line integral is actually the work done in moving an object along C in the positive direction. Okay, the word object is loosely defined. We can say more about this. We can put more definition to this object, but let's just let it be the way it is for now. So we already have this formula. We already developed it. Copy, paste here. So this integral is equal to that. All right. And another notation for this integral is A to B f dr. That's it. So this is sometimes called dr, like that. Okay. Let's do an example. Let's do some examples. So I would like us to evaluate the integral of v dot t ds, the vector line integral, with f equals y minus x on the following oriented surfaces or oriented paths on R2. So the first path is the quarter circle from Q equals Q10 to P01, right? So we're going from Q, which is 1, 0. This is our Q, to P, 0, 1, P. All right? Like that. So that's the orientation, positive orientation. So this is our C here. So we can define C with R of t. R of t would just be cosine t, sine t, and t is going to go from 0 to pi over 2, right? So that means we can find our r prime of t, and our r prime of t is negative sine t, cosine t, and then that means that the absolute value or the magnitude of r prime of t is just equal to 1. Now, we want to find the integral. We want to find this integral, vector integral, vector line integral, along the line integral of a vector field. That's what we want to find. So this is going to give us, we already know that this is going to be the integral from a to b. A in this case is 0, b is pi over 2, of f of r of t times r prime of t, or dot r prime of t dt. Okay? So I'm going to put a here and b, but we know what a is. This is our a and this is our b, like that, a and b. And b. Okay? So when we plug in everything, we have 0 to pi over 2. F of r of t, what is f? F is this function, right? When we plug in sine of t for y and cosine of t for x, what do we get? We end up with sine t minus cosine t, and then cosine t. And then we'll find the dot product with negative sine t, and then cosine t, and then we have our dt. So this is f of r of t, and this is r prime of t. Okay. Okay. All right. If you perform this dot product, you're going to get 0 to pi over 2 of negative sine squared t plus sine t cosine t plus cosine squared t. All right. And then dt. That's what I got. And this, the first and the second term, the first and the second term can be combined to give us something. All right, I'm going to tell you what I have. I want you to simplify the inside or the integrand. If you simplify it, you're going to end up with cosine 2t plus 1/2 sine 2t. So how do you go from this to this? That's the question you need to ask yourself. All right. And after doing this integration, I got 1/2. 1/2. Okay. So this step has to be filled. You got to use some, the step from this line to that line. You got to use some trig identities. I want you to use trig identities. How do you express sine squared t? How do you express cosine squared t? Okay, half angle formula might do it. All right. Okay. So now I want you to try something. B. So the first one, we're going from the quarter circle from Q to P. Now, no, from Q to P. How about from P to Q? How about from P to Q? From P is 0, 1 to Q. Q is 1, 0. And then, so that is that. Yeah, you're going this way. This direction, C. So you're going P, 0, 1, and Q is 1, 0. All right. So if the first one is C, the second one is negative C. Okay. All right. I want you to do it yourself, but I'm going to tell you the answer. Try it yourself. I'm going to put a little try this. Not just the stuff, the whole problem. Try this. Oh no. Oh no, oh no. All right. So I'm going to tell you that this integral, instead of C, is now negative C of f dot t ds. After doing the computation, you're going to get negative 1/2. Just the opposite of what you got. All right. So for scalar vector field, right? It doesn't matter the path. If we're going the opposite direction or the forward direction, we get the same integral. But for, scalar line integral, we get the same value. But for vector field, the line integral over a vector field, so in general, the integral, the line integral f ds is equal to negative the line integral negative c f dot t ds. Sorry, the line integral f dot t ds over c is equal to negative f dot t ds over negative c. Okay, or we could, let's put this here, same thing, but let's put c over here. Okay, provided f is a vector field. Okay. All right. Okay. So another problem I want us to solve is this. I want us to now look at, this is also you. This is you trying a bunch of things. You have a lot of things to work on this video. So you want to go the path. Let me make it in dark. The path from P to Q via 2 line segments. through O, through the origin 0, 0. What do you mean? Or what do I mean by this? I want to go like this. So this is Q, and this is P. Okay? I want to go from P to O, and I'm going to call this C1, and then I want to go from O, all right, to Q. I'm going to call this C2. Well, let's make C2 green. Okay. All right. So you'll be dealing with two line segments. There'll be two C's. So you want to compute f dot t ds over C, but then you'll be going from C1 f dot t ds. You'll be adding f dot t ds over C1 and f dot t ds over C2. You'll be adding both of them together. All right. So why are we doing this? We're doing it because the line from P to Q along the axis, along the y-axis and x-axis, is not smooth. It's not smooth. So we have to break it up where there is an edge. There is an edge here. All right? You don't go that, you just don't go, you don't pass through an edge. It has to be smooth. So that's why you're doing it separately. You're breaking it up into two line integrals. All right. So that is all I want you to try, and we're going to see each other in class. All right.